This video is a brief introduction of the review paper about the phenomenon called image or acoustic polaritons in thin van der Waals crystals that was published in 2022. Polaritons are quasi-particles born out of coupling between the free space photons and collective oscillations of charges in the polaritonic material. Polaritons in atomically thin van der Waals crystals are highly confined and thus are able to provide strong light-matter interaction. At the same time, their evanescent fields penetrate beyond thin material boundaries and thus are exposed to external manipulation. Van der Waals crystals have been shown to support various types of polaritons in a broad frequency range, depending on the type of collectively oscillating charges. For example, coupling of light with collectively oscillating free electrons produce plasmon polaritons, and coupling to the lattice vibrations of polar dielectrics produces phonon-polaritons. This review focuses on a newly discovered polaritonic phenomenon that arises due to the screening of polaritonic near field by a highly conductive substrate. The so-called acoustic or image polariton is formed when the near field of polaritonic wave is screened by a closely located PEC-like mirror. This can be easily realized with thin van der Waals crystals, which can be separated from the mirror by a thin dielectric spacer or placed directly on the mirror. In such configuration, polaritonic mode is equivalent to a mode with a symmetric out-of-plane field component supported by a two-layer system of 2D crystal or a twice thicker dielectric slab. At the same time, modes with antisymmetric out-of-plane field component cannot exist in such a system with mirror symmetry. The first image polariton was demonstrated at terahertz frequencies in graphene, separated from gold by a thin HPN spacer. The image plasmons in graphene are usually called acoustic plasmons due to their mostly linear dispersion. Later, acoustic plasmons in graphene were demonstrated at mid-infrared frequencies in arrays of nanocavities with recurrent breaking mode confinement factors. Such a huge mode confinement is possible because acoustic plasmons do not experience geometrical cutoff similar to the gap plasmons in thin metallic slits. Therefore, the confinement factor is limited only by the spacer thickness, which in reality cannot be thinner than a single atomic layer of van der Waals dielectric, such as HPN in these cases. At the same time, phonon-polaritons have been shown to reach very high quality factors, by far exceeding those of graphene plasmons. Image phonon-polaritons were first observed in van der Waals dielectric HPN and later in biaxial crystal alpha MO3. Since phonon-polaritons are supported by dielectrics, presence of the dielectric spacer between the crystal and the mirror is not necessary. However, spacer allows for the existence of additional high-order image modes. However, phonon-polaritons are mostly localized within the dielectric slabs, which makes them less accessible in the limit of a single-layer crystals. Therefore, the real space observation of ultra-confined image polaritons has been possible only in graphene. Importantly, ultra-confined acoustic graphene plasmons enter the non-local regime, where plasmonic momentum becomes comparable with that of free electrons in metal and graphene. Such a non-local response of image plasmons provided a new platform where quantum phenomena can be directly probed within macroscopic samples. Our review paper nicely summarizes the analytical models and experimentally observed physical properties of all image polaritons reported by the time of publication, not limited to graphene and HPN. Table 1 summarizes these results and highlights the limiting cases. Interestingly, image phonon-polaritons have been reported to have much larger effective mode indexes and quality factors, but lower mode confinement factors. For the complete information about image polaritons, please refer to the published manuscript or contact the corresponding author.